Okay, we're looking at this problem, which is for what values of the constant c is this piecewise function f continuous for all real numbers? Taking a look at this constant function, this piecewise function, it is defined by polynomial functions to the left of 1 and to the right of 1. So that means it must be continuous at every real number except possibly at 1. This means the only thing that we need to actually be concerned about is making sure that f is continuous at 1 itself, which is to say we need to check the left-hand limit and the right-hand limit as x approaches 1 and make sure that those two one-sided limits agree with each other. So I'm going to go ahead and write that out here to make sure that we have all of that written in our neat and tidy homework. And now I'm going to calculate the left-hand limit and the right-hand limit and figure out what c value is going to make those two limits agree. So I'm going to calculate the left-hand limit. So the limit as x goes to 1 from the left, from values of x that are less than 1 of f of x, is, I'm going to rewrite that limit thing. X goes to 1 from the left. So if x is less than 1, then we are using this first formula for the defining f. So I am going to put in that formula. This is c times x squared plus 1/2 x. And calculating the limit of that as x approaches 1 from the left, we can use direct substitution, since that is a polynomial, which is continuous everywhere. So this is the same as c times 1 squared plus 1/2 times 1, which is c plus 1/2. So now calculating the right-hand limit as x approaches 1. So as x approaches 1 from the right, from values of x that are greater than 1, of f of x. I'm going to rewrite that limit notation. X approaches 1 from the right of, now if x is greater than 1, I'm in this part of the domain, so I'm going to use the second formula for the definition of f. So I'm going to put in that x cubed minus cx. And so this is a polynomial. I can evaluate that limit by direct substitution. So this is 1 cubed minus c times 1 is 1 minus c. So in order for f to be continuous at 1, we need to have those two left-hand limits and right-hand limits coincide. So let me write that. In order for f to be continuous at 1, we need c plus 1/2, that's the left-hand limit, must equal 1 minus c. That's the right-hand limit at 1. So solving that, we have c plus 1/2 equals 1 minus c. Let's add c to both sides and subtract 1/2. So that's add c and subtract 1/2, add c and subtract 1/2, and I have 2c has to equal 1/2. That means c has to equal 1/4. Okay, so that means that if I have f of x equals, I have to look back at this. What is it? 1/4 x squared plus 1/2 x. 1/4 x squared plus 1/2 x. If x is greater than or less than or equal to 1, and x cubed minus 1/4 x. If x is greater than 1, this should be continuous for all real numbers. So let's take a look at this on Desmos. I have put this function, this piecewise function, into desmos, into an equation line. And just to let you know how desmos handles piecewise functions, so I start with that that curly brace, just like we have in written notation. And we start by actually defining the part of the domain. So I say for x less than or equal to 1, I put a colon, and here is the definition of the function for that part of the domain. And then I have a comma, and then I can list, all of the other formulas for each other part of the domain. So in this case, if x is greater than 1, colon, this is the definition of the function. Now I put in that c, which is an unknown, and desmos gives me an option to create a slider. And so right now it's putting the slider at 1. So this is the function that is 1x squared plus 1/2 x for x less than or equal to 1, and x cubed minus 1x for x greater than 1. And you can see that there is a break here at x equals 1. All right. And if we drag that slider, we can see that there's a discontinuity between those two pieces, a jump discontinuity, for all of these different values of c. But there is one place where those two different branches meet up. And that looks like it is between 0.2 and 0.3. And we calculated it as 1/4. So if we put this in 1/4, then we can see those two branches actually meet up exactly. And if we zoom in, we can see they don't break.